All right, I just want to recap what we went through today so that you're ready for what's coming up in the next lecture. So this is basically just a summary. We want a general solution to a differential equation of this form, right? And then we said, okay, well, we guess x equals e to the lambda t. And when we do that, we get a quadratic polynomial in lambda. And anytime you have a quadratic polynomial, there are three things that can happen. Either you have real distinct roots, or you have repeated roots. So just one root, let's just call it lambda. Or you have no roots, but actually we'd rather introduce complex numbers, and we'll say we have complex roots. Let me just write alpha is lambda is some real number plus minus some real number times the imaginary unit. And this we will get into later. Then what we did today is we analyzed, from the three cases, from the three possible situations, we analyzed this one. So what did we find? We found that then the general solution is x of t equals e to the lambda 1t, is c1 e to the lambda 1t plus c2 e to the lambda 2t, where c1 and c2 are the two free parameters. They're like the plus c that you get when you integrate for the general solution. And this works because these functions are linearly independent functions. That's why this is the general solution. And that is everything we did today, basically. That's it. Next time, we will cover case 2, and the main difference that you'll see there is that we only have one solution. And if you pretend it's two solutions, if you say, well, it's like lambda 1 equals lambda and lambda 2 equals lambda, well, then those are not linearly independent, right? They're in fact the same vector, so they're not linearly independent. So that wouldn't be a way to get the general solution. And so there's a problem here. The problem is need more solutions. We only have one solution. So yeah, we can be like, okay, c e to the lambda t is a solution for any choice of constant c, but that's not enough to satisfy a pair of two equations that appears in a single initial condition setup. So we need more solutions so that we can be like c1 something plus c2 something. We need those 2 degrees of freedom. And then with complex roots, actually, we will get this to work nicely. These will be linearly independent, but the problem is we wanted a real solution, and we're going to end up getting a complex valued function. So we need a real solution. That will be the problem there. And there is, it turns out that if you just allow solutions to be complex briefly, and then, pass through, sort of solve your initially real problem. There was nothing complex about the problem at the beginning, right? When we said we want the general solution to this, we want real solutions. It's a real sort of problem. But it turns out that if you pass through some of the complex numbers theory, then come out the other side with something real, that will work. So we'll be using complex numbers as sort of an intermediary between this totally real setup and the totally real solution that we want to end up with at the end.